All right, we're going to get started with a new unit, and this is going to be all on sequences and series. You may have done some of this work in Algebra 2 or geometry, so again, it might be partially review, but then there may be, our pre-calc twist on something like that. So an infinite sequence is a function whose domain is the set of positive integers. The function values a sub 1, 2, 3, 4, all the way to infinity are the terms of the sequence. If the domain of a function consists of the first n positive terms only, it is a finite sequence. Basically, if it has an ending point, it's a finite, and if it's infinite, it does not end. So if we were to look at, say, the function, here, let's call it a sub n equals 3 plus negative 1 to the n power. Again, I would try to find, all right, I want to find the first term, the second term, the third term, the fourth term, and the fifth term. So what I'm going to do is I'm going to go through, and every time I see an n, I'm going to plug in a 1. And then solve. 3 minus 1 equals 2. And then for this time, I'm going to plug in, every time I see n, I'm going to plug in a 2. This gives me 3 plus 1 equals 4. And then for this one, every time I see an n, I'm going to plug in a 3. So you can kind of see that, hey, our pattern is going to start repeating itself. So then this one's going to equal 2 as well. So we can find terms of a sequence. Okay, the questions are to, or the question is asking us to write the first 5 terms of the following sequence right here. So again, I would just go through plugging in every time I see an n. I'm going to plug in my 1 if it's the first term. Negative 1 over 2 minus 1 equals negative 1. A sub 2 equals negative 1 squared over 2 times 2 minus 1. 1 over 4 minus 1 equals 1/3. A sub 3 equals negative 1 to the third over 2 times 3 minus 1. 1/5. Fourth term, negative 1 to the fourth power. So while this one is kind of similar to our last example, it's slightly different because it's repeating, but it's also getting smaller. And it's alternating between positive and negative. So if you again kind of notice when we have this negative 1 to the n power, that may force, parts of our equation or parts of our answers to flip between positive and negative. Finding the nth term of a sequence. So write an expression for the apparent nth term of each sequence. So if we took the following 2 expressions, said we've got the expression 1, 3, 5, 7, ... I would say, all right, for my terms are increasing. My term is like 1, 2, 3, 4. And then that's my n value. And then my terms are returning my values of 1, 3, 5, 7. We're going to call this a sub n. So it seems that each term is 1 less than 2 times n. So the apparent nth term, whatever my term is, I'm going to double it and then subtract 1. So again, I'm looking and I'm saying, hey, this is a difference of 2, difference of 2, difference of 2. Okay. If we look at a slightly different example, let's say B is 1, 2, 3, 4 to to the nth power. Again, this is like my n terms, or my n, and then my terms. What I'm returning is 2, 5, 10, 17. So I'm going to say it seems that each term is one more than the square of n. So the apparent nth term is a sub n. So again, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So I'm taking whatever my squared number is, and I'm adding 1 to it. I'm adding 1. The Fibonacci sequence, a recursive sequence. So recursive means that we use the previous term. Ugh. So in order to find the 10th term, we need the 9th term. In order to find the 100th term, we need the 99th term. So the Fibonacci sequence is kind of a classic example of this in math. So if we take our first term, we call it 1. We take our second term, we call it 1. Then we can get a formula where if I want the whatever term, I take k minus 2, so the second to last term, and I add it to the last term. And again, k has to be greater than or equal to 2. So how does this work? If a sub 0 is 1, okay, so if I want to find a sub 3, I need to find a sub 1 plus a sub 2. All right, well, I know these. 1 plus 1 equals 2. So a sub 3 is 2. Now if I want to find the fourth term, I need to take a sub 2 plus a sub 3. 1 plus 2 is 3. If I want to find the fifth term, I need to take the third term plus the fourth term, which is going to be 2 plus 3 equals 5. 5 plus 3 is 8. 8 plus 5 is 13. So it goes on and on and on and on and on. So I wanted to expose you to the Fibonacci sequence because it is a classic sequence, recursive sequence like that. And the last kind of idea that we're going to touch on for this lesson is about factorals. So some very important sequences in math involve terms that are defined with special types of products called factorials. A factorial can be described as, you use an exclamation point. And so this means I take all my previous terms and I multiply them together. N minus 1, and then my last term is n. As a special case, so the one rule, so 0 factorial, so something that looks like 0 with an exclamation point equals 1. So that's kind of the one rule that we need. So again, 0 factorial equals 1. 1 factorial is just 1 times 1, or just 1. 2 factorial, 2 times 1 is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24. And 5 factorial equals, again, 5 times 4 times 3 times 2 times 1, which is 120. So this number can get very large, very fast, due to just the nature of factorials. All right, so writing the terms of a sequence involving factorials. So if you get a sequence that looks like this, 2 to the nth power over n factorial. We're going to start at n equals 0. So again, as I go through, I'm plugging these in, and I am using my knowledge. Any exponent to the power of 0 is 1. 0 factorial was that weird case that we said was 1. So a sub 1. That's 2 to the first power over 1 factorial. 2 over 1 equals 2. A sub 2. 2 squared over 2 factorial. 4 over 2 times 1 is 2, which is 2 again. A sub 3. 2 to the third power over 3 factorial. 8 over 3 times 2 is 6, which can be reduced to 4/3. And the last one is just 2 to the fourth power over 4 factorial. Gives me 16 over 24, which is 2/3 reduced. All right, and then the last kind of idea with factorials is evaluating them. So if we think about, all right, how do we evaluate them? The thing we need to really think about is how division works. So if I look at the example, 8 factorial over 2 factorial times 6 factorial. If I were to write this out, so let's do that, equals, on the top, I have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all over 2 times 1 times 6 times 5 times 4 times 3 times 2 times 1. Now, when I look at this, I can cancel out all types of things. Cancel out, cancel out, cancel out, cancel out, cancel out, cancel out. So really, all I have is 8 times 7 over 2 times 1, which is going to equal 28. So you can cancel out a lot of things in your expression to save yourself a lot of calculator time. 2 factorial times 6 factorial, all over 3 factorial times 5 factorial. So again, 2 times 1. You can do 1 times 2 or 2 times 1. It doesn't matter. The order of multiplication doesn't know. I just like working backwards, but it really doesn't matter if you want to do 1 times 2 times 3 times 4. Again, the order shouldn't matter. And then we have 3 times 2 times 1 times 5 times 4 times 3 times 2 times 1. So when I'm going through, I'm canceling out what I can. I'm going to get 6 over 3, which equals 2. All right, let's just do one more. One more for good measure. This one's a little bit different in form. N factorial over n minus 1 factorial. So again, whatever it is, 1 times 2 times 3 times 4 times that. Eventually, I'm going to get to the second to second to last term, and then the last term. And then on this one, I'm going to do the same exact thing, but I'm just going to eventually get to the last term. So when I go through and cancel, 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 all I'm left with is n.